Hi class, today we'll be working on Chapter 14, Wireless Networking. Let's do a quick introduction to wireless networking. Wireless networks use radio frequencies, RF waves, to communicate between different devices. So we're using RF waves to communicate between different devices. This enables flexibility and mobility. Wireless uses nearly all of the same protocols as wired networks. So we're using almost all of the same protocols as we would on a wired network. The main difference comes in the first two layers of the OSI model. Wireless differs from wired networking in types of media and protocols for transmitting and accessing data. Wi-Fi standards. As we mentioned before, Wi-Fi is by far the most widely adopted wireless networking type today. It's been around since the late 1990s. IEEE 802.11 is the standard that covers Wi-Fi. There's a bunch of subcategories for it. So there's some things like 802.11G, 802.11AC, 802.11AX. There's a whole bunch of these different subcategories. We're going to talk about some of that today. A little more on 802.11. The standard defines how wireless devices communicate, also address communication security. The first iteration, sort of Wi-Fi 0, 802.11-1997. This was the first iteration of the 802.11 standard for Wi-Fi. It established baseline features common to all Wi-Fi standards. So wireless networking cards, configuration software, compatibility to run multiple network styles, and how transmission works. Those are just some examples of the type of things that we're setting standards for. Wireless Ethernet Network Interface Cards, NICs. Essentially, they have the same function as wired network interface cards, except for they transmit using radio waves. Networking capabilities are built into many modern devices. However, if it's not, it's usually pretty easy to expand that capability. We have internal PCIe wireless network interface cards. We also have external USB wireless network interface cards that are readily available. Wireless access points. These interconnect wireless network nodes with wired networks. So they interconnect wireless network nodes with wired networks. At a basic level, a wireless access point essentially just acts like a hub. It is a layer 1 device at the most basic level. However, you can have wireless access points that have higher levels of functionality. So you could have a wireless access point that has the functionality of a switch or a router built into that device. This over here is an example of a wireless access point that has higher level functionality built into it, capable of working as a switch or a router. I guess I should say switch and a router. It's capable of functioning as a wireless access point, a switch, and a router all at once. Wireless network adapters need two key pieces of software to function: wireless device drivers and wireless configuration utility settings. So some important settings that you may, or important information you may need to know about your settings, be things like link state, signal strength, wireless networking modes, security encryption, and power saving options. Over here, we have on the right, we have an image of the wireless client configuration utility for Windows 10. If we look close, we can see some key information like the SSID, the protocol, security type, network band, network channel, etc. Wireless network modes. We're going to talk about two main types. Ad hoc mode, also called the peer-to-peer mode, uses a mesh topology, works well for small groups of computers or temporary networks. Here's a diagram or an image showing a ad hoc mode type network. We see it's kind of a mesh topology there. The other mode that we're going to talk about is the infrastructure mode. Uses one or more wireless access points to connect the wireless network nodes. So it's going to be similar to a star topology type network. We have a couple key terms to think about here, which is BSS, basic service set. This is when it's serviced by a single wireless access point, and then an extended service set when we're using two or more wireless access points. Infrastructure mode requires more planning. You got to consider things like wireless access placement to ensure that you get adequate coverage. You generally use infrastructure mode for business networks or for sharing dedicated resources like a centralized database. Real-world wireless networking range is kind of hard to pin down. Usually you'll see things advertised in the ballpark of 150 feet to about 300 feet, but in the real world, there's a lot of mitigating factors that can affect your range. Solid objects, EMI, things like that can greatly diminish the overall range of your wireless network. Basic Service Set Identifier, BSSID. Essentially, the BSSID is just a naming scheme for wireless networks. The most basic infrastructure mode. So for infrastructure mode, the BSSID is the same as the MAC address of the wireless access point. So again, for infrastructure mode, the BSSID is the same as the MAC address for the wireless access point. In an ad hoc mode, the IBSS nodes generate a random 48-bit string that will be used as the BSSID. Again, this will function and look essentially the same as a MAC address. Service Set Identifier, SSID. This is just another level of naming for the network. When you pull up your laptop or mobile phone, whatever it may be, and you're looking at the wireless networks that are available in your area, each of those, that is just the SSIDs for those networks. So that name that you see, that is the SSID. If you go to a coffee shop and you look at you're looking for that network to connect to, and you see coffee shop network, that is the SSID for that network. When you go to the college and you see whatever campus network, that is the SSID for that. Again, home network, same thing. So all that is the SSID is just the name that you see, or you'll generally see when you're trying to connect to a wireless network or Wi-Fi in your area. Here are some of the kind of key stats that you need. So sometimes it's called the network name, contains 32-bit identification string. Every Wi-Fi device must share the same SSID to communicate in a network. The SSID broadcast shows all available networks. By default, most wireless access points will broadcast their SSID. However, you can configure them to choose not to broadcast their SSID. So when someone pulls out their phone or whatever device and is looking for wireless networks in their area, your network will not show up. It is still working and still functioning as a wireless network. Just by default, without taking any extra steps, they won't be able to see that your network is available. And sometimes that can increase the level of security for your network a little bit. It's not bulletproof. It's not something that can't be dealt with, but it just adds an added level of security for your network. Extended Service Set Identifier, ESSID. So again, this is something that most devices are not going to call it an ESSID. They'll just refer to this as an SSID, but it's still a concept that's worth exploring. It's for Wi-Fi networks that use multiple wireless access points. So again, multiple wireless access points, we're calling it an extended service set. Each wireless access point is connected to a central switch or switches to become part of a single broadcast domain. So we're having multiple wireless access points become part of a single broadcast domain. Clients connect to whichever wireless access point has the strongest signal. One clever bit of technology is if you're roaming. So if you're on your mobile device and you move from one wireless access point to another, they should be able to have a process that kind of seamlessly makes that transition for you. Again, you won't often see the term ESSID on most devices. They'll usually just refer to it as an SSID, but it's important to kind of use the term to visualize or understand that concept of what's going on here with an extended service set. That was a lot of key terms very, very quickly, so I wanted to run back through some of them. Basic Service Set, BSS, Extended Service Set, ESS, Basic Service Set Identifier, BSSID, Service Set Identifier, SSID, Extended Service Set Identifier, ESSID. You may want to take a screenshot of this, or maybe make flashcards of each of these terms here. Transmission frequencies. When we're dealing with wireless, there's definitely a lot of potential for interference from other wireless devices or just other things in the environment in general. So this is something that the IEEE 802.11 standards cover. It's also something that most governments around the world cover pretty strictly. The two frequencies that the original 802.11 standard used were 2.4 gigahertz and 5 gigahertz. It's important to note that this 5 gigahertz thing is separate from the mobile phone or the mobile 5G standard. So the 5G is more of a generation standard, and this is just a frequency, the 5 gigahertz frequency. Transmission method. The original IEEE 802.11 standard used spread spectrum radio waves, transmits data in small discrete chunks, uses different frequencies within different ranges. There's 3 different spread spectrum methods. We're going to look at all of these: DSSS, FHSS, and then OFDM. That stands for the DSSS It stands for Direct Sequence Spread Spectrum, FHSS, Frequency Hopping Spread Spectrum, and OFDM, Orthogonal Frequency Division Multiplexing. So direct sequence spread spectrum sends data simultaneously on different frequencies, uses about 22 megahertz of bandwidth, capable of greater data throughput than FHSS, more prone to interference than FHSS. Frequency hopping spread spectrum sends on one frequency at a time, constantly shifts or hops from one frequency to another frequency, uses less bandwidth than DSSS. Orthogonal frequency division multiplexing. This is one of the newer methods. It's better at dealing with interference. It's used on the majority of modern 802.11 networks. Channels. A channel is a portion of the spectrum. So for example, for the 2.4 gigahertz band, our 802.11 standard defines 14 channels that are 20 megahertz each. That doesn't necessarily mean every single country will use all of those channels that are potentially available. So as I mentioned before, this is something that's fairly heavily regulated, and it's regulated differently by each government of each different country. So for example, in the US, the 2.4 gigahertz band may use 11 channels, or channel 1 through 11. Here's some best practices. You generally don't use adjacent channels on nearby wireless access points. You'll usually want to space them out as much as possible. So you'll get something like 1, 6, and 11 used very frequently. And as I mentioned earlier, most governments strictly regulate which bands and which channels within each band that Wi-Fi systems can use. The 5 gigahertz band offers many more channels than the 2.4 gigahertz band, approximately 40 different channels for the 5 gigahertz band. The 802.11 versions that use the 5 gigahertz and 6 gigahertz band use automatic channel switching. So as we mentioned previously, with the 2.4 gigahertz band, we have to kind of manage channels efficiently to optimize communication. We want to space out those channels manually in order to make sure that there's less interference between two wireless access points that are using channels that are really close together. However, when we're using the 5 gigahertz and 6 gigahertz bands, those will automatically manage that aspect of the communication process for us. CSMA/CA, Carrier Sense Multiple Access with Collision Avoidance. Wireless devices cannot detect collisions. So previously, when we were talking about wired networks, we talked about CSMA/CD. So Carrier Sense Multiple Access with Collision Detection. When we're talking about wireless access, we cannot detect collisions, so we try to do something else, which is avoid them, collision avoidance. There's two collision avoidance methods, DCF and PCF. So as technology has progressed and moved along, we've had different variations of the 802.11 standard. We're going to go ahead and run through some of the different versions of the 802.11 standards that we've had. One important thing to note before we jump into it is they have fairly recently retroactively added a second name that they think will be a little easier to kind of manage and remember. So instead of the whole long 802.11a, 802.11b, all that kind of stuff, they just have added different Wi-Fi generation names to them. So the previous one that we talked about, the first one, 802.11-1997, would be Wi-Fi 0. This next one here would be 802.11b or Wi-Fi 1. Well, I think part of the intention was to make things a little bit easier for everyone. Ultimately, it just kind of resulted in the network engineer community now has to remember two names for every version. This was the first widely adopted Wi-Fi standard. Data throughput was around 11 megabytes per second. The range was approximately 300 feet. The downside uses the crowded 2.4G frequency, more likely to have interference coming from other wireless devices. Next, we have 802.11a or Wi-Fi 2. Different from all other 802.11 standards, operates at a less crowded 5 gigahertz frequency, greater throughput with speeds of up to 54 megabits per second, had a short range of 150 feet, was never as popular as the 802.11b standard. Incompatible with 802.11b. One kind of confusing thing that I want to emphasize here, A came after B. I know that's weird. A came after B. 802.11a is Wi-Fi 2. 802.11b is Wi-Fi 1. This is a table that kind of quickly summarizes key points from the standards that we talked about. 802.11-1997, 802.11b, and 802.11a. So we have the frequencies that each of them operate at, the spectrums they use, the speeds, the range, and the compatibility. Up next, we have 802.11g, also known as Wi-Fi 3, up to 54 megabits speed, same range as 802.11b, about 300 feet. It was backwards compatible with 802.11b. A wireless access point can service both 802.11b and 802.11g. However, 802.11g networks run in native mode when 802.11g devices are connected. So when you have an 802.11g network using only 802.11g devices, you will get that 54 megabit speed, so that much faster speed. However, if you're mixing devices, so if you're using the older and the newer stuff, it will run in what is called a mixed mode, where things drop down to a lower speed of 11 megabits per second max. So again, it can support both devices, but if you do, you get that lower speed. 802.11n, Wi-Fi 4, brought several improvements, faster and newer antenna technology. Standard required multiple antennas to use MIMO, implementation of multiple input, multiple output, MIMO. Implement channel bonding. So the big kind of thing here, the big gimmick here, is that you're combining multiple channels. So you can create, you can take two 20 megahertz channels and combine them into one 40 megahertz channel. That would greatly increase the throughput. A little more on 802.11n. The throughput was up to 600 megabits per second theoretically. Many wireless access points employed transmit beam forming, use multiple antennas to get rid of dead spots. Downward compatible with 802.11b and g, but it would cause slowdowns. Again, no free launch here. Uses modes to handle slowdowns, so you had 3 modes to choose from: legacy, mixed, and greenfield mode. 802.11ac. This is called Wi-Fi 5, and it's an expansion of the 802.11 standard. It incorporates more streams, so we can get this this big 80 megahertz and 160 megahertz channels, and that gives us much higher speeds. It only operates at the 5 gigahertz band. So a quick recap on the key stats or key specs for those standards we just talked about: 802.11g and 802.11n, and then 802.11ac. The last one we're going to talk about is 802.11ax, called Wi-Fi 6. This implements orthogonal frequency division multiple access, OFDMA. Brings improvements to high density areas, so stadiums, conference halls, etc., called Wi-Fi 6 in the 2.4 gigahertz and 5 gigahertz bands, called Wi-Fi 6E in the 6 gigahertz band. So we're using 2.4 gigahertz, 5 gigahertz, and 6 gigahertz bands. The range is approximately 300 feet, give or take, and it vastly improves throughput. So I don't think the book stressed how much of an improvement the standard is over previous standards, but it is much, much better at handling multiple people or large crowds of people trying to access a wireless access point all at the same time. Many devices are still not capable of using this technology. Many wireless networks have not been upgraded to adapt to this technology, but it is definitely a massive improvement over previous generations. This is a quick table that summarizes the 802.11ax standard. All right, that's all I have for this week. The main focus, again, is to make sure you understand all those 802.11 standards. There is another section in this chapter that covers wireless security, and I definitely think it's important to read through that.